Welcome to the Path to Transactions. Today we're going to talk about the global logical clock. As you guys know, Mongodb is coming out with multi-document ACID transactions in 4.0, and this is one of the exciting projects that helped us get there. Today I have Misha with me, an engineer on the Sharding team, and we're going to walk through this project. So I'm going to pass it over to you, Misha.
Hey there. So I'm Misha. I worked on this project with the rest of the team for about a year, and we have built two things. One is a global logical clock, which runs in MongoDB starting version 3.6, and then on top of it we have built causal consistency support. And global logical clock in general allows to establish global snapshot, which is very necessary and helpful for building up the transactions, which is going to be our next station.
Right, because you need a global snapshot in order to have snapshot isolation across the sharded transaction.
Yeah.
Great.
We need to have a consistent view of all data across all shards.
Right.
So let's start with just a very brief overview of what MongoDB is, in case you don't, if you want to refresh. It's distributed, sharded, replicated database. And internally it supports NoSQL. So it consists of multiple nodes, and they have different roles. There are storage nodes, which can group together into replica sets to provide reliability of the data. So it's kind of fault tolerance. If one of the nodes goes down, the other one will basically picking up the role of the master node, which allows to do writes. And the horizontally data could be partitioned using sharding, which means that shard 1 and shard 2 will have different ranges of keys. So therefore, when query comes, it will be routed to the appropriate data shard, and it allows to distribute the load across multiple logical units.
So looking at this diagram, the blue boxes represent replicas, where they contain the same set of data. And the orange boxes represent shards, which contain a distinct partition of data. So they don't share the same pieces of data.
Yes,
Great.
Exactly. And the green boxes are routers which do not hold any data. And their task is to know where to send the queries, which are coming from clients, which are here marked as an app server. It's on the top. So causal consistency simply says if event A causes event B, then this order will be noticed on all nodes in the server. That's about it. So there's a lot of research which happens about that, and it goes back into 1978, where Leslie Lambert introduced the first way to provide causal consistency, essentially ordering event in a distributed system. And so basically what he wrote, and this is a very, very influential article in distributed systems actually. Basically, he introduced Lambert Clock. And Lambert Clock is just a counter, it's a scalar value which assigned to each event. And the event is either processing data on the node or sending data to another node. So it's exchange or processing of the data. And essentially, it's a way of numbering those events, the way that if event A causes event B, then the number on event A will be less than number on event B. The converse is not true. If number of an event A is less than number of event B, doesn't really mean A causes B. It could mean anything.
Right.
But that was enough to start ordering events on the system. And when we were working on that global logical clock, we basically were looking in different variants of Lambert clocks. And obviously, since 1978, there were a lot of research in this area. There's different variants of that. There are vector clocks, for example. There are ways to implement clock synchronization if there is certain hardware available, using atomic clocks. And there's some quite recent article which describes the hybrid logical clock, which are very similar to the Lambert clock, but they provide ability to bound to physical time. And this implementation also happened to be very close to our way we keep the time on the replica sets in the uplog. So it was very easy for us technically to implement that and convert existing model from just incrementing what we call uptime, which is time in the uplog, to convert it to the logical time, which unlike uptime, which is local to the replica set, will be global to the sharded cluster. But of course, to make it global for the sharded cluster, we need to build some form of exchange of this data. And now this is what another diagram which I'm going to show. There we go. So in general, cluster time, this is like our term internally, for this global logical clock, has just two rules. And those two rules are quite different from, I think, at least the article or academic research. And rule number one is that we separate events from sending and receiving messages. So we consider events only what changes durable state of the system, meaning it's any write into the up log. So this is the event in MongoDB cluster time meaning. And therefore, only those events can tick, meaning increment, the logical clock. This is rule number one.
Right, and the only node or process in MongoDB responsible for interpreting those changes is the MongoD, right? So the MongoD is the one who increments time.
MongoD primary.
MongoD primary.
Yeah, so time. Because Mongo is a replicated set, it has one primary, which always take writes, and secondaries, which replicate those changes.
Right.
Only primary has the ability to tick the clock.
Right.
Everybody else here follow rule number two, which is keep track of the greatest seen logical time and always distribute it. So that's about it.
So in every request that I send from any other process, I just send the latest time I'm aware of.
Yeah.
And then what happens is the node that receives that jumps to that time.
Yeah, exactly. So, and this is pretty much where research stops.
Yeah.
But with production system, and as I said, I mean, not so many systems actually even were looking into causal consistency implementation, which makes sense for end users. And once we started working on this, we realized that there is one scenario which was, I mean, at least I haven't seen it being covered, which is very dangerous for our database. Essentially, like assuming the client is not a good client, but some malicious attacker, competitor, whatever, who just wants to break the database. And with like naive implementation, which I was just talking about, the clients, they send some value and then uplog puts this value into the database. It's very easy to break it because it's a number.
Yep.
So it's
a number with the value cap, right?
It's essentially, it's like 64 bits.
Yeah.
And it's possible to just send the maximum value -1, so it will be able to increment it, meaning tick this, right? And after this, that would be basically end of the game because there's no way to increment, and that means because if this has been majority committed to the database, the only way to fix it is actually to unload the data, clean it manually, reload. So it's major outage.
So all of those requests from the normal clients would fail in this case, right? Because it's saying I've already incremented to the end of time. I can't increment anymore, so I can't accept
Not
the write.
just to clients. We do have sometime internal writes as well. So basically, the database will be like really broken majorly in a big way. So it's absolutely no go. So we started thinking of how would we fix it? How would we make sure that while we are like open source database, we assume that anybody can operate it. We assume that users should not, the clients are not always fully trusted, like basically meaning that they're inside some authentication perimeter and stuff like this. It could be anybody, like using the driver who sends the request, and we want to make sure those are working fine with causal consistency and doesn't break the database. And so our solution was just use the signature. So we generate the signature for cluster time, which is generated by MongoDs, and therefore client just cannot change it, because in order to change it, they need to have an access to the private keys, which are securely generated and kept inside the MongoD, like either primary, if it's a replica set, or on the config server, but they're inside the perimeter, so we can trust that users cannot get them easily. And that's basically how we implemented that. And we, of course, worried a little bit about the performance overhead, because it basically means that every message has to be validated and every message has to be signed. But we came with some optimizations which
mitigate this risk.
Which mitigate the processing overhead and still keep the time safe.
Yeah.
And I think there would be, some materials which will go into these details if you're interested. But the bottom line is that it's not taking too much resources to provide this level of security.
Right.
So that was basically how we built the logical time and what the major challenge and what is a major outstanding feature we have comparing to academic research or other implementations.
So one of the questions that I have before we end this video is around a common question that we get. Why did we not choose the vector clock? That's one of the popular ones right now in the industry. So
well, vector clock is basically the difference between vector clock and Lambert clock is that vector is a vector, Lambert is a scalar, meaning that vector essentially passing the clock which ticks on each shard, and each shard allowed to have the different value. And therefore, when we need to synchronize the time in one shard, sometimes it has to generate the no operational right, just some value has to be put into the up log in order to generate the value of the logical clock, which will make this shard consistent with the rest. So this is a major, I would say, major implementation detail which concerns our users sometimes. So vector clock do not have this problem because they do know they could detect the consistency without doing this upright, but at the expense of putting in our case it's just one number, and it will be number equal to number of shards. And since we are should be able to scale to hundreds of shards at least, it's just not going to work. It will be a huge overhead in communication. It will introduce major performance hit.
Because you'd have to have a value per shard, where this is a global value, a singular global value. The clock wouldn't scale to a large-scale sharded deployment.
Yeah, so in this case, it's with the signature, it's approximately, I would say, 50 bytes. And over there, it will be 5K or something like that. I'm just not going to work.
Yeah. It's not feasible to send with every request and every operation, which is how this gossiping works.
Yeah, we usually have some workloads where network is getting saturated if users really driving the load with small inserts, for example, small updates. And if we just make messages 10 times bigger, it will not help them.
Yep, that sounds good. Thank you, Misha, so much for your time on this, walking us through.
Well, you're welcome.